in experiment.
We don't know yet.
Why is light so fast?
Like, it sounds so simple.
They had no idea.
But now the data speaks.
I find this not only refreshing, but at some level astounding.
Nature.
Welcome back to the Nature Podcast. This week, could red mud make green steel?
And spotting signs of long COVID in people's blood. I'm Shamini Bandel.
And I'm Benjamin Thompson. Aluminium is one of the most important metals in the modern world. Tens of millions of tons of it are produced every year, a figure that is growing. New aluminium, i.e. not recycled, is predominantly derived from an ore called bauxite, and part of this process produces a lot of waste with an innocuous sounding name: red mud.
Red mud nowadays is a burden because we have about 4 billion tons piled up around the globe.
This is Isnaldi Souza from the Institut Jean Lemour in France.
It is actually a big problem because red mud is associated with pollution, contamination of soil, contamination of water. Then sometimes also catastrophes happen when the dams broken apart and spreading tons and tons and tons of red mud over cities, for example.
Currently, only about 3% of this toxic red mud is used for anything, mainly construction. The majority of it ends up in landfills, pumped into vast lakes or stored in dried mounds, all posing major environmental risks. But what if red mud could be used for something productive and sustainable? Well, Isnaldi thinks it could, because of its composition.
Specifically because of iron oxides. Could be up to 60%.
Red mud is red because it is chock full of iron oxide, essentially rust. And iron oxide is used to make iron, which is used to make steel, which is used to make, well, everything. Isnaldi and his colleagues wondered whether they could get the iron out of red mud to make better use of this waste product and potentially provide another massive benefit to producing steel as well.
Normally, we can consider that for each ton of the steel that we produce nowadays, we are emitting 2.1 tons of CO2 to the atmosphere. I would say that about 8% of the total CO2 emissions on the globe comes from the steel industry.
Steel production emits billions of tons of carbon dioxide every year, and much of this happens when iron oxide is heated in a blast furnace using fossil fuels. Superheated carbon monoxide reacts with the iron oxide, stripping away the oxygen, leaving behind iron, which can be made into steel, producing carbon dioxide. A lot of work has gone into trying to make this process greener. For example, by using hydrogen gas instead of carbon monoxide to strip oxygen out of the iron ore, producing water rather than carbon dioxide. It's hoped that approaches like this could be pivotal in producing so-called green steel, made with minimal emissions. So, where does red mud come in? Well, in previous work, Isnaldi showed that superheated hydrogen plasma could be used to extract iron from an ore called hematite. And this got him thinking.
What would happen if I, instead of using hematite, but red mud in my furnace, what would be the outcome? Could we obtain iron out of it as we did for hematite? So that was the inspiration. And of course, motivated by the sustainable metallurgy practices, we are trying to target the real problems nowadays in our society.
Isnaldi and his colleagues processed red mud in an electric arc furnace. These use electricity rather than burning fossil fuels to melt whatever's in the furnace, and they are already used on an industrial scale in steelmaking. Isnaldi's, however, was only about a metre tall and in a lab. Inside their mini arc furnace, they placed small samples of dried red mud and flooded the chamber with a mix of hydrogen gas and inert argon gas. Then they switched it on. The electric arc melted the red mud, exposing the iron oxide, along with several other metal oxides it contains, and split the hydrogen into plasma, which got to work, binding to the oxygen in the oxides and releasing metal. But in particular, it favoured the iron.
Among the total quantities of oxides that we have inside the liquid, iron oxides are the one with the less affinity to oxygen. So this means that all oxygen that will be collected by hydrogen are the oxygen that's actually sitting close to iron. So that's why then iron coalesces in the form of nodules as a liquid metal, then it sinks to the bottom.
They ended up with small chunks of iron at the bottom of the furnace, but that isn't all that happened. Other reactions altered the remaining red mud.
The pH, which was super alkaline, let's say around 11, 12, decreases to nearly neutral, like 7. And of course, the remaining oxides, which are not iron oxide, they react among themselves to form this dark slag.
The cooled waste slag is a black, glassy-like substance containing nodules of shiny iron. Isnaldi says this iron is pure enough to be used in steelmaking, and the neutralised slag would be easier to handle if it were used in construction. And the whole process produces H2O in the form of steam rather than CO2. Overall, the team showed that they could extract 2.6 grams of metallic iron from 15 grams of red mud, which they were very pleased with.
If you make theoretical calculations and you calculated the maximum amount of iron that we can extract, is something very close to this experimental value that we obtained in our lab.
Isnaldi is working to figure out the best conditions to get the most iron. But he sees a lot of promise in the approach and calculates that it could be scaled up to industrial levels in an economically viable way. However, it's important to remember that this is still a relatively small lab-based demonstration. Here's Chenna Rao Bora from the Indian Institute of Technology, Kharagpur, who wasn't in the research team.
Yeah, I'm really impressed. They introduced a new process for the production of iron making from a waste material. So in that way, this process is really good. However, I want to see its applicability in commercial scale. So for that, we need to at least study this process in a pilot, because then only we can come to know the techno-economics of the process. They did the preliminary economic calculations and they found that this is economically viable. But however, if you produce in the pilot scale, you can get better numbers.
Chenna also highlights that at a commercial scale, there's a lot of dust and vaporized metals produced, along with unused hydrogen. And making sure they can be dealt with safely or reused needs to be considered in order to ensure the process is as sustainable as possible.
Most of the companies, governments also want to minimize CO2 emissions from their steel production. So by 2050, several companies already pledged to produce carbon neutral steel. So if the process works, then it can change the steel making process. So for that, we need green hydrogen.
Green hydrogen is made by splitting water using renewable energy. It's currently expensive, but it's likely to play an important role in lowering the emissions associated with refining iron ore, and therefore in the production of sustainable or green steel. Processes like the one Isnaldi described are reliant on hydrogen, and while they may produce minimal direct CO2 emissions, if the hydrogen they use is made using fossil fuels, then there will still be substantial indirect emissions. There's a long way to go, and a lot of uncertainty surrounding when and if green steel can effectively be produced. But the world will continue to need both steel and aluminium, and recycling or reusing waste material, although helpful, will not be enough to feed that need. However, Isnaldi hopes that work like his could help.
At least we could decrease the harmful impacts that we are actually causing to nature, specifically related to the position of red mud in open nature and landfills. And we will be very close to a circular economy by taking wastes and extracting the best of it.
Isnaldi Souza from the Institut Jean Lemore in France there. You also heard from Chenna Rao Bora from the Indian Institute of Technology, Kharagpur. You can find links to Isnaldi's paper and a News and Views article written by Chenna over in the show notes.
Coming up, a new model tries to predict whether someone's going to develop long COVID by looking at proteins in their blood. Right now, though, it's time for the research highlights with Dan Fox.
A new generation of advanced geothermal systems capable of storing energy that can be released as needed could boost power production from the Earth's internal heat. Geothermal power plants make electricity using steam or hot water from natural underground reservoirs to drive turbines. Enhanced geothermal systems work in much the same way, but with an artificial reservoir created by injecting fluid underground. Previously, most studies assumed that these enhanced systems produce power at a constant rate, but now a group of researchers has investigated the potential of taking a more flexible approach in the western United States. In the team's model, enhanced geothermal plants pump fluid into their reservoirs when other variable energy sources such as wind are sufficient to meet demand for power. When demand outstrips supply from these sources, the plants then extract those fluids to generate electricity. Their results suggest that this flexibility would make the plants more economically attractive, and the capacity of flexible enhanced geothermal systems in the region could account for 37% of peak demand. Steam over to Nature Energy to read that research in full. An origami robot made of textiles can crawl forward like a snake. Snakes' winding movements have long inspired robotics researchers, but the linear motion that allows the reptiles to creep through tight spaces without shifting sideways has been relatively unexplored. But now researchers have designed a concertina-shaped robot to mimic this motion, using pieces of laminated fabric folded into segments. During linear motion, the skin on a snake's belly stretches, but the skin on its back does not. To replicate this, the researchers equipped the base of each segment of the robot with air pouches that expanded when inflated. This stretching caused origami scales on the robot's base to tilt onto their points, creating friction. When the pouches deflated, the friction pushed the segment forward. Inflating and deflating each segment in sequence allowed the robot to crawl on a range of surfaces, reaching a top speed of around 18 centimeters per minute. The team behind the design say it could be used in situations that demand movement in close quarters, such as search and rescue operations, but further work will be needed to add steering capabilities. You can read that research in full in Device.
Finally on the show, it's time for the briefing chat, and we're going to discuss a couple of articles that have been highlighted in the Nature briefing. I've got a story on long COVID this week, and it's a Nature article I've been reading based on a new study published in Science, which basically was looking at proteins in the blood, took blood samples from people who had never tested positive for COVID-19, so never had it as far as they knew, people who had it, and people who had long COVID, both sort of 6 months long, and some people who still had symptoms 12 months after first testing positive. And they basically compared the blood samples from all these groups.
Right, and of course, we haven't talked about COVID for a while. And long COVID then is this condition that seems to come with an absolute multitude of symptoms and can last a very, very long time.
The problem is that it seems to be a bit of a mystery. So there's a quote from a physician in this article saying that long COVID is at the moment, pretty much impossible thing to treat. And we don't know exactly what causes it, and we don't know how to identify it. So this is just one study, and I should say that this isn't a huge sample size. They've got 113 people who've had COVID before, of whom 40 had long COVID, of whom 22 still had the symptoms 12 months later. So not huge numbers. But what they did do was then analyse over 6,000 proteins across multiple blood samples. And they were samples from the participants when they had COVID and 6 months later.
And what was the aim of this then? What were they looking for in these blood proteins?
Well, differences between the groups, and that is what they found. They found significant differences in the kinds of proteins that you had, particularly in patients who had fully recovered compared to patients who still had the symptoms. And what they were also interested in is which precise proteins these were. And they seemed to be a lot of proteins involved in the immune response, blood clotting and inflammation.
And I guess then these could potentially be used as markers to say if someone is experiencing long COVID, which of course can be particularly debilitating.
Yeah, so that's definitely one thing is, okay, if you've got these differences, can those differences be used diagnostically, as it were? So they fed all this data into a machine learning program and then created this sort of predictive model. You could give it blood samples. And the idea of the model is that you could give it a blood sample of someone with a current sort of COVID infection, and it would be able to predict from the blood proteins at that point whether that person would go on to have this 12-month long COVID. And the model seemed to perform pretty well when they gave it sort of new data to test it.
Although, as you say, small numbers of people.
Yeah.
So what happens next here?
Well, the other interesting thing about this, and this is also kind of a pro and kind of a con, in that it doesn't actually tell you why long COVID is happening. It doesn't actually explain away all these different symptoms, which is kind of a real problem for actually developing treatment. So being able to predict and be able to spot these differences isn't on its own that useful. But when you look at the differences that they found, interestingly, maybe they could provide some clues as to maybe not a super simple underlying mechanism, because long COVID seems really complex, but some clues as to the causes. And there were some really interesting things they found, including proteins to do with blood clotting. There was a protein where its presence on white blood cells indicates abnormal clumping, which could contribute to microclots. And they found this was highest in these people with 12-month long COVID. And that's interesting because there's this theory that maybe tiny blood clots are the cause of some long COVID symptoms. And we reported on that last summer, how some people are really interested in this microclot theory, saying like, well, maybe this could explain everything. And other people are sort of like, we don't really have the data yet, not really sure. Worries about people trying home remedies and things that aren't proven and things like that. So it's definitely providing some more clues as to this basically sort of mystery condition at the moment.
And still one that is perplexing many researchers. So an interesting finding, and hopefully one that can lead to something useful for people who are experiencing long COVID. But let's move on, Shamini. And I've got a couple of stories this week. But the first one, well, it's an update. It's an update on something that you and I talked about last week.
Oh, it's part 3 of the ongoing sample container saga, is it?
That's right. It's the OSIRIS-REx sample container saga part 3, and it's more good news. So just a very brief update, I guess, in the briefing chat. And it's a story, as you say, we've been following for the past few weeks. And I think this will probably be the last one we do for a while. But yes, OSIRIS-REx's sample container has been opened. Last week we talked about how there was a couple of stuck bolts and the researchers managed to get those off, and all that was left to do was kind of crack the canister, take the lid off, and we said, when's it going to happen? And it happened at the end of last week. So NASA, once again, very helpfully waiting for us before we could record this show, which is great. And yeah, they've cracked it open, and thankfully the canister is full of bits of the asteroid Bennu.
I wonder, are NASA getting in on the sort of live streaming game? Because with all the drama of them trying to get into this, I feel like you could just have a camera set up in the lab to see them working away at this thing.
No live stream, but there is an amazing photograph.
Okay.
So 2 researchers captured a still image using manual high-resolution precise photography and a semi-automated focus stacking procedure.
Right.
Okay, this is according to NASA's website. And they've taken this amazing photograph from the top of the sample chamber. I'll send it to you now so you can see it. And it looks kind of like the door to a bank vault, I suppose.
Yeah,
it's kind of a
does.
circular thing. And inside you've got this kind of dark grey material. And this is asteroid. And there's dust and kind of larger kind of pebble-sized things. And we'll put a link to that in the show notes so the listeners can see it as well. But yeah, that's it. They managed to do it. And I think what happens next, and maybe we'll follow this story later in the year, is that NASA are going to release a catalogue of all the stuff that they've got. And from that, researchers and institutions can submit requests to actually get hold of this material.
Oh, great.
But anyway, let's move on to the other story that I've got today. It's another space story, actually. It's something that happened at the end of last week. And it's Japan becoming the 5th country to manage a soft landing on the moon. And this is interesting because it's a precision landing, okay, to touch down closer to its target site than has ever been done before. It's not all good news though, right? Like, it does appear that this lander did land.
Great.
But since then, it's had some problems, and in the first few hours, it was kind of shut down.
Wait, so when you say precision landing, I guess I never really thought before much about how precise a moon landing has to be. How much more accurate was this one than previous soft landings?
You know, that is a great question and something that I didn't know the answer to until I read this article in Nature. And so for context then, this craft is the Smart Lander for Investigating Moon, or SLIM.
Great name.
And it's a mission of Japan's space agency, JAXA. And its nickname is the Moon Sniper. Okay, so that gives an idea of what it's all about. And so the idea for this mission, the primary aim of this mission, was to land on the moon within 100 metres of where it was intended to go. And its target area was this place called the Shialei, I'm not sure, crater on the south of the moon's equator. Okay, so within 100 metres of where it was due to land.
Okay.
And this is a fairly big leap from previous efforts that have been a few up to a dozen kilometres away from where they aimed at, right? So we are talking a big change in accuracy here. So I followed this on Friday afternoon UK time when it was coming down, and telemetry data suggests it did touch down within its target area as planned. Obviously the exact location is being figured out, and it did so in a very clever way, right? It used this vision-based navigation technology. Okay, so it kind of visualized the surface of the moon as it was going along and compared this to maps that it had on board to work out exactly where it was. But then things went a bit sideways. So rather than landing 4 feet down on the ground as other craft have done, the plan was that SLIM was designed to hit a 15-degree slope outside the target crater, first with one leg, and then the idea was that it was kind of tip forward and stabilise on the rest of its legs. Okay.
I'm tense just hearing about this plan.
And it seems to have not gone entirely according to plan, right? And observers suggest that maybe it might have rolled during touchdown, but this isn't a crash landing. It has done a soft landing on the moon.
Okay.
But it appears that as a result of whatever's happened, the solar panels are facing the wrong way, so it can't charge up its batteries.
Oh, no.
Yeah, so a few hours after it landed, its battery was super run down, and so JAXA actually switched off this battery. It was currently at 12%, I believe. So it's kind of sleeping, this probe, but it might be woken up, right? They're hoping that at some point the sun will be at the right angle to hit the solar panels where they are now, which wasn't obviously the plan, and potentially charge the battery up enough.
But I guess they don't know precisely enough when that might be because they don't know exactly what it looks like in that spot.
Yeah, so a bit of a watching and waiting game, I think, which is a shame. And so on the face of it, that's kind of disappointing. But actually, I think that needs to be tempered with the success of it doing what it was supposed to do. But if they manage to get the battery to charge up, I think it does have a little bit of science on board, right? It's only got one scientific instrument, which is this camera, which is to look for a mineral called olivine, okay? And it wants to compare olivine on the moon to olivine on Earth, which might offer some new insights into was the moon part of Earth, that sort of thing. And there's a few other bits as well, which were a bit of a shame. Apparently there's 2 small robots that were due to be jettisoned during the landing procedure, and they were supposed to take pictures of the lander. Now, one of these was a little hopper, and one of these was a little sphere, okay, that could change shape.
Oh my god!
And what's cool is that this was designed, as I understand, in partnership with Tomy, the toy maker, who make the Transformers toys.
There's 100% going to be a film about these little robots and their struggles. I can literally see it now.
We don't exactly know what's going on with them. Apparently the hopper might have worked, but again, we'll wait and see exactly what's going on there. But overall, I think this mission can be considered a success, right? And this landing technology can potentially be applied to other missions. And a successful soft landing is really hard, as we've discussed many times, okay? So Japan really joins a select group of countries that have managed it. And, you know, just a few weeks ago, at the start of the year, a commercial attempt, the US Peregrine craft failed to soft land on the moon. And the moon is big business for a bunch of different countries and companies. There's another commercial landing attempt next month. And later this year, China is going to launch its Chang'e 6 mission to return samples from the far side of the moon. And of course, we have the Artemis program and a bunch of other stuff too. So a lot for us to cover, I'm sure, over the months and years of lunar exploration.
I thought last year was Year of the Moon, but this year, even more moon stories. I should be looking forward to them. Listeners, links to all these stories are going to be in the show notes, and a link to the Nature Briefing itself, which is a regular email newsletter with a collection of the top science stories.
Well, let's call it there for this week's episode. And of course, if you want to get in touch with us, you can. We're on X @Nature Podcast, or you can send an email to podcast@nature.com. I'm Benjamin Thompson.
And I'm Shamini Bundell. Thanks for listening.